All right, linearization. So when you think about the big concepts we've got, we have continuity or continuous. This is what continuous means when you write it out. This is what continuous means when you think about it. Close inputs result in close outputs. Differentiable. Here's what differentiable means. Oops. But as we've been saying over and over again for the past 2 chapters, differentiable means locally what? Locally linear. Okay? That's what it means. And those are the 2 big properties we've been talking about here for the first half of the course. So what happens in section 4.6 is we just kind of rebrand it, because we had our tangent line formula, y equals f prime of a times x minus a plus f of a. So we had this, we used it for the last couple chapters. The first thing they talk about in this, in section 4.6, is they rebrand this and they call this the linearization of f at x equals a, and they call it L sub a of x. That's all they do. So when they talk about the linearization, they're just talking about the tangent line. They're just calling it something a little different. And I think back in the day, I actually called it L of x when we were doing it anyway, L for line. So let's do an example. So here's the definition there for you. Find the linearization of f of x equals 1 plus root at x equals 0 and use it to approximate the square root of 1.01. Okay, so if you're going off to engineering, physics, things like that, you'll see this kind of thing happen like all the time. All right, especially with this function. So here's our f of x, square root of 1 plus x. And it said they want us to find L0. Okay, so L0 of x is, by definition, the tangent line at 0. So it's going to be f prime of 0 times x minus 0 plus f of 0. And so we're just going to construct this the same way we constructed the tangent line. So we're going to do our f of 0, plug in 0 for x, and we get what? 1. Now to get f prime of 0, I need f prime of x. So I need the derivative of the square root of 1 plus x. And how are we going to take the derivative of that? Bless you. That's 1 plus x to the what? 1/2. And now what's the derivative of something to the 1/2 power? And then chain rule would kick in. We'd have to multiply the derivative of what's in by the derivative of what's inside. What's the derivative of what's inside now? 1. So f prime of 0 would be this. Once again, the most common mistake you see is people forgetting to actually plug in the number here. All right? So they get a linearization that's not a linear function. Remember, when this is all said and done, your linearization should work out to be like an mx plus a b thing. You follow? If you've got powers of x other than x to the first, then you forgot to plug something in somewhere. You follow? That's why I like to just break it down step by step like this. All right, so L naught of x equals f prime of x, which is a half, times x minus 0 plus f of 0, which is 1. So this simplifies to 1/2 x plus 1. And how do we check using Desmos if this really and truly is the tangent line? What should happen? If I graph my function, and I graph my linearization, near the point when x equals 0, and you zoom in, what should happen? Yeah, they should look the same. Whoop, there it is. Behold the local linearity. So once again, what that means is near x equals 0, f of x, we can approximate f of x by the linearization. That's local linearity there. Okay? So f of x is the square root of 1 plus x is approximately 1/2 x plus 1. All right. So once again, is there anything new? This is just a nice kind of callback to, you know, section 3.1 and section 3.2. Just calling it linearization. So let's look at what they want us to do with that. Use L naught to approximate the square root of 1.01, and then we're going to use it to approximate the square root of 0.8. So if this kind of thing looks familiar, it is, because we did this a couple chapters ago. So let's say I want to do the square root of 1.01. First off, I need to write this as the square root of 1 plus something, because I got to figure out what the x is. You with me or not? Okay. So this is 1 plus what? Was it 1.01 or 1.1? I forget. Yeah, 1.01. Are we good with that? So this is now the x. So according to my linearization, the square root of 1 plus 0.01 is approximately equal to 1/2 0.01 plus 1. Oops, I put that line there. And we can almost do this in our head, right? What's 1/2 of 0.01? 0.005, so this would be 1.005. Okay. And we can see how good of an approximation this is. We can plug in square root. Whoops. There it is. So our linearization did a pretty good job. Make sense or not, folks? Now, how would we use this to approximate the square root of 0.8? Well, I got to write this as the square root of 1 plus something, because this is what my function is. You follow? So 1 plus what gives me negative 0.8? Negative 0.2, good. So this is what's going to go in for my x now. So that's approximately equal to 1/2 times negative 0.2 plus 1. And once again, you can do this one in your head. That's going to be what when it's all said and done? .9. Okay, and you can check to see how close that is. All right. Any questions? Make sense or not, folks? Let's look at number 3. Find the linearization of f of x equals cosine x at x equals pi over 2 and use it to approximate the cosine of 88 degrees. Okay, so now we're looking at f of x equal cosine x. We want L pi over 2 of x. By definition, that's the tangent line, pi over 2. So I need the slope at pi over 2, f prime at pi over 2, times x minus pi over 2, plus f of pi over 2. The f of x is cosine of x. So what's the f of pi over 2? That's the cosine of pi over 2, which is what? So think about unit circle. Pi over 2 is right there. Cosine is the what coordinate? X. So what's the x coordinate on the y-axis? 0. What's f prime of x? What's the derivative of cosine? Negative sine. So what's f prime of pi over 2 minus sine of pi over 2? What would be the sine of pi over 2? 1. So this would be what? Negative 1. And so I put that together for my linearization. F prime at pi over 2, negative 1, times x minus pi over 2, plus f of pi over 2, which is 0. So we can simplify here, distribute that negative. It's minus x plus pi over 2, or pi over 2 minus x, depending on how you want to think about it. So basically what that says is that if your x is near pi over 2, you get the cosine of x by just taking pi over 2 minus x. So this says if x is approximately pi over 2, f of x is approximately the linearization at pi over 2. In other words, the cosine of x is approximately pi over 2 minus x. Now what they give us is they give us the cosine of 88 degrees. And as we mentioned before, when we derived the formula for the derivative of sine and cosine and all that stuff, we needed to use those limits, sine x over x, 1 minus cosine x over x. And for those limits to work out to be the friendly numbers of 1 and 0, you had to measure those angles using what? Radians. So when we go to plug in the 88 degrees, I can't plug 88 into there. You follow? This x is measured in radians. So I got to change it to radians. So 88 degrees, how do I convert that over to radians? Yeah, so there's an exchange. So here we go. Here's your dimensional analysis. So Dr. Thomas would be so proud of us today. All right, let's see. Degrees will cancel. What do we got going on here? I guess there's you could do a 2, and then I could do a 2 again. So 22 pi over 45. Does that look okay? So the cosine of 88 degrees, which is the cosine of 22 pi over 45 radians, is approximately pi over 2 minus 22 pi over 45. And if we want to get a common denominator here, it would be what? 90? So it'd be 45 pi's in the first one minus how many pi's in the second one? 44. So we're left with pi over 90. So the cosine of 88 degrees would be approximately pi over 90. Whoops, and we can check that, of course. Any questions on this example? See what's going on here, folks? It should look awfully familiar because we did it quite a bit. So there we go. There's the approximate value for you. I don't know why it's not highlighting. And then there's the actual retail value. Okay. So once again, what you're going to see, like I mentioned, a lot of these come up when you're studying motion of the pendulum or what's called simple harmonic motion in physics and engineering. You will often see a reason to approximate square roots. This way also the trig functions. Example 4 and example 5 are videos. This is just looking at the sine at 0, and this is looking at a more general function, 1 plus x to the p. We talk a lot about this function in Calc 2. We spend at least a day on it and expanding it. In fact, I know Emily's a physics major. One of the problems we're going to talk about in Calc 2 on Thursday uses this kind of thing, although we have to go to the next level in Calc 2, to approximate the time dilation factor that helps GPS satellites account for the time difference between their orbit and Earth. Because we're at the bottom of a gravity well, they're at the top spinning around. So there's time flows differently for objects higher up in the gravity well moving versus us. And GPS has to account for that so we can take the turns at the right time. So all that relativistic stuff that seems like science fiction, it happens every single day on your phone. It's pretty wild. But there's an approximation they use for that, using this kind of thing. All right, let's look at example 6. The amount of money in dollars in an account after 10 years, if invested at an annual interest rate R compounded monthly, is given by this formula. So this is, usually you run across this in college algebra or pre-calculus. We'll revisit this formula a little bit at the end of the course, and then in Calc 2 we take this formula and take a limit to get it to the PERT formula. It says find the linearization of A about R. Okay, so A of R, the amount is a function of the interest rate. 300, 1 plus R over 12 to the 120th power. And they want A of A0. Okay? Now if you think about it, interest rates, like 2%, 1%, 0.5%, 1% is 0.01, right? 0.5%, 0.005. So all these interest rates are numbers close to 0 anyway. So it makes sense to linearize this, because if you imagine trying to actually calculate this, I mean, of course you've got calculators and stuff, but the 120th power can be a challenge even for machines, depending on what's going on in there. If your R is really, really small, the calculator might not be able to distinguish what's going on in that from 1. You follow? So we're going to use the linearization. So once again, linearization, we need A prime of 0 times R minus 0 plus A of 0. So we have our A of R. So let's plug in A of 0. And what is A of 0? When R is actually 0, what do you get? 300. Which makes sense. If you invest $300 with 0% interest, then your account balance is always going to be what? $300. Okay. Now let's look at A prime of R. So I need to take the derivative with respect to R of 300 times 1 plus r over 12 to the 120th power. So now we go back to our derivative properties. What can we do with the 300? Bring it out, 300. Now I'm taking the derivative of something to the 120th power. So what's that? 120 times that thing to the what? 119th. And then chain rule kicks in, times the derivative of what's inside. What's the derivative of 1? Plus the derivative of r over 12. See if we can sneak this in. What's a prime of 0? So once again, when you plug in r equals 0, you just get 1 to the 119, which is 1. I've got 120 over 12, which is 10, times 300 is 3,000. Any questions on a prime? Or then what a prime of 0 is? We all good with that? Remember, think of r over 12 as 1/12 r. Just factor the 12th out and you got your derivative there. All right, now we put all it together. I'm sorry, not a naught, it's L naught. I don't know why I called it a. There we go. So L naught at r is a prime of 0, which is 3,000, r minus 0, which is r, plus 300. And so local linearity says if r is roughly equal to 0, so if r is close to 0, a of r can be well approximated by L of r. In other words, 300 times 1 plus r over 12 to the 120th power can be well approximated by 3,000 r plus 300. And when it comes to computation, if you look at what's going on the left-hand side, we'd have to take r divided by 12, add it to 1, and then take it to the 120th power. That could be a challenge. You follow? That's just, there's a lot of opportunity for small decimals to get lost in that calculation. Whereas on the right-hand side, you're just multiplying by 3,000 and adding 300. You see the difference? Find and interpret L of 0.2 and L of 0.5. So L naught at 0.2 would be 3,000 times 0.02 plus 300. And once again, we can kind of do this in our head, I think. Because think of 0.02 as 2 over 100. So this would be what? 360? So what does that mean? We plugged in 0.02. 0.02, this is an R value. What comes out is an A value. You with me or not? So this says when R is the interest rate, so 0.02 corresponds to what rate? Zero 0.02 is how many percent? 2%. The amount in the account will be approximately, because once again, This is an approximation of the actual value. Be approximately how much money? $360. Make sense or not, folks? So what's nice about the first part of this chapter, this section, is it's literally just a reminder of tangent lines and how they can be used to approximate things. Stuff that we talked about way back in 3.1 and 3.2. It's that concept of local linearity. All right, the second part of the section deals with differentials. And differentials is just another rebranding. So if you look at the linearization, which once again, linearization is nothing more than your tangent line. And then you just rewrite it. Then another way to think about what's happening with this linearization is we're at a function that's differentiable. If it's differentiable, that means it's automatically continuous. You follow? So we know that if x is close to a, the f of x is going to be close to f of a. So notice we have that f of a here, and we can think of this as a correction term, an approximate error. So it's going to be f of a plus a little bit. So for example, when we plug this in, this was your a of 0, and this would be your correction factor. You follow? So here it was 300 plus 60. So 300 was the value if the rate were 0. And then if the rate is 0.02, we started at 300 and added that $60. You with me or not? So this is what differentials are. So this would be the differential. Okay. If y equals f of x, so if we get the dependent variable involved here, then we know that if x is close to a, we know that y would be close to f prime of a times x minus a plus f of a. Or in other words, y minus f of a would approximately be f prime of a times x minus a. Is everyone cool with the algebra there? Now what this represents is this represents the actual change in y on the curve y equals f of x. That's the actual change delta y. What this represents is the change in y on the tangent line, because this is your slope of the tangent line times your change in x on the tangent line. You with me or not? So the change in the tangent line, this is what's called dy. So that's called the differential in y. The differential in y is the change on the tangent line. And I got a picture here, we'll tie all this together. So here's the definition. dy is defined to be f prime of x dx, where dy is called the differential of y, thinking of y as the dependent variable here. Y is a function of x. The dx is the same as delta x. This is called the increment in x, because x, once again, is the independent variable. So in the expression y equals f of x, x is the independent variable, Y is the dependent variable. And so in this section, that's what the dx stands for. It's really no different than the delta x. So local linearity, another way to express local linearity is that the change on the curve can be approximated by the change on the tangent line. In other words, the delta y can be approximated by the dy. So local linearity, reprise, is if you have y equals f of x, the actual change in f of x, which is the actual change in y on the curve y equals f of x, can be approximated by the differential, which is the slope times your dx. So once again, this is slope of tangent line times delta x. So if x is approximately equal to a, so that the delta x, which is x minus a, is close to 0, f of x is approximately equal to f of a plus the dy. Or dy would be f prime of a times your x minus a. So you're literally just taking a part of that tangent line and calling it something else. That's it. Okay, that's it. We're going to start at f of a, and we're going to tack on this correction factor. What's the correction factor? The slope of the tangent line times change in x. So I went through, I created this diagram here, which has all the stuff on it. I had to spell out the word delta because Desmos didn't have a delta. Okay. But here's the delta x down here. So this is where delta x is. Here's where the delta y is. And here's where the dy is. So that's the change and versus the delta y. And you can see as you get closer and closer to this point of tangency, you can see that the delta y and the dy get close together. Right? So that's just another way to express the local linearity. So let's see how this gets done in practice. Oh, I will mention this. Historically, right, when the Western world started to codify calculus ideas, remember the Leibniz notation? Well, check it out. That's how we define the differential, and that's consistent with dividing both sides by dx. You with me or not? And when this was first, when like Newton thought about these things, the dx, the increment dx, think of that as an infinitesimal change in x. And so, whereas the slope delta y over delta x is a change in y over change in x, the dy and dx represent an infinitesimal changes, very, 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 very small changes. Okay. So we've got this. Okay. So let's work through an example. Suppose f prime of 5 is negative 2. If dx is 0.2, find dy when x equals 5. So dy is f prime of x dx. So dy would be f prime of 5 dx. F prime of 5, they told us, was negative 2. dx is 0.2. That's negative 0.4. So what does this mean geometrically? Is you're over here at x equals 5. F prime at 5 is negative 2. What's f prime mean? F prime is the what? Slope. So here's whatever's going on. I don't know where f of 5 is. I just don't know. It could be above, below, wherever. All I know is that the slope there is a negative 2. You follow? And the dx is 0.2. That means I'm looking at what x value? Right, so remember dx is delta x. That would be x minus 5. So if x minus 5 is 0.2, x must be what? 5.2. You follow? So that means if I come over here to 5.2, wherever the f of 5 is, up here, if I move over 0.2, I'm going to be down how far on the tangent line? It's negative, so I'm going to be lower. It's going to be roughly 0.4 less. Make sense or not, folks? Okay. The slope's negative 2. I'm moving over 0.2 units. That means on the tangent line I've gone down 0.4 units. Since the function is differentiable, that means it's locally linear, so the actual value of f of 5.2 is going to be roughly 0.4 units lower than f of 5. Do you see what's happening with the picture? Okay. So, let's go back. Use the fact that f of 5 equals 6 to approximate f of 5.2. So f of 5.2 is going to roughly be f of 5, right? This is what they told us. This is our known value plus our differential when x is 5 and the dx, the delta x, is 5.2 minus 5, which is 0.2. So f of 5.2 is roughly 6 plus the dy, which we got to be negative 0.4, which is 5.6. Do you see how all the parts are coming together to give us this calculation? You have a differentiable function, which means it's locally linear. So f of 5.2 should be f of 5 plus a little bit. That little bit we find by going to the tangent. Use differentials to approximate f of 4.5 using what is known about f of 5 and f prime of 5. Okay, so f of 4.5 is going to be roughly equal to f of 5 because that's the one I know about. Plus my dy. Now for my dy here, I'm going to use the fact that x equals 5, and the dx, which is the delta x, is going to be 4.5 minus 5. So if I think about the graph, 4.5 is over here. So what's the delta x then? If I'm starting at 5, what direction do I have to go to get to 4.5? I have to go to the left, so negative 0.5. So my dy would be f prime of x dx. In this particular case, it would be f prime at 5 times negative 0.5. So negative 0.2 times negative 0.5. A negative times a negative is a what? Positive. And then half of 0.2 is what? 1. So does it make sense? Once again, on the graph, if the slope is negative if I move to the left, should I be getting to something a little bigger? Does that make sense? And how much bigger we approximate using the slope there. Wait, what was the f prime? Did I screw that up? The f prime was what? -2, excuse me. So yeah, that's why everyone's looking at me. F prime is -2, not -0.2. This makes it even nicer because this is what then? That's a positive what? 1. So f of 5 they tell us was, let me get this right, f of 5 they tell us was 6 plus 1, so we get 7. Okay. So f of 4.5, once again, that's roughly f of 5 plus the dy. F of 5 was 6, the dy was 1, so we get 7. You see how all the pieces come together? So it's, once again, it's still linearization. It's just framed a little differently. So I like to think of this process as I look at the f of the unknown, right? I think, well, let's see here, this. Yeah. So this is f at what I don't know. That's approximately equal f at the point that I do know, plus the dy. The dy is the derivative at the point that I know, times the difference of the unknown minus the known. Make sense or not, folks? All right, example 9 is a video. Oh, let's do example 8, and then example 9 is a video. So example 8 says, let f of x equals the square root of x. Find an expression for dy. Use differentials to approximate root 9, knowing the fact, root 11, knowing the fact that root 9 is 3. So here we go. So this actually goes way back to when we first introduced derivatives. This was like, I don't know if it was the square root of 11, but it was the square root of something. If I asked you to mentally estimate the square root of 11, you would say, okay, 11 is really close to what perfect square? 9. The square root of 9 is 3. Since 11 is a little bigger than 9, the square root of 11 would be a little bit bigger than 3. So it would be 3 plus something, right? So this should take you back, way back to section 3.1, which sounds like it would be a long time ago. In fact, it was only what? I don't know, 2.5 weeks ago? 3 plus something. That something, that's your differential. You follow? That's that differential. So we find an expression for dy. dy by definition is f prime of x dx. The square root of x, how do we rewrite that to make it easy to take the derivative? X to the half. What's the derivative of x to the half? Perfect. That's our expression for dy. Okay. So I want to know what the square root of 11 is. Okay. So 11 is our unknown. Okay. I don't know what's happening at 11. So I'm going to approximate it by the square root of something I know. And the closest thing that I know is the square root of who? 9. Plus the associated differential. So it's going to be the square root of 9, 3, plus something. So let's figure out what that differential is. We have an expression for the differential right here. So what I need to plug in for x, I want to plug in the known value. And then for the dx, that's going to be the unknown minus the known. Because that's how far away I am from the known value. You follow? So I'm just going to rewrite this because we're out of room here. So what's our known value here? I know about what x value. The known value is what? That's 9. That's the x that's getting plugged into the function. The known value is 9. What I'm trying to figure out is the unknown value, which is when x is 11. So my dx, which is my delta x, would be the unknown minus the known, 2. So once again, if you think, it sometimes helps to think geometrically. Here's 9, here's 11, here's the square root curve doing its thing. You follow? I'm going to basically use the local linearity at 9 to help me figure out what's going on here at 11. So from 9 to 11, I need to go 2 units to the right. You follow? So I'm going to take that slope. The slope of the tangent line is going to be this part right here. That's your slope. And that's your change in x. So I'm going to plug in the 9, because 9 is the number I know about. And this will give me the slope at 9 times 2. That's going to give me how far up we're going on the tangent line, and that should approximate how far up we're going on the curve. You follow or not? We'll do a Desmos here at the end just to make sure we're all good. So what's 9 to the minus 1/2 power? Well, what's the minus, dude? That puts the thing where? In the denominator. You can see what happens to the 2's. They do what? And what's 9 to the 1/2? That's also known as the what of 9? And so this is what? 1/3. So the square root of 11 is roughly the square root of 9 plus 1/3. So that's 3 and 1/3, or 3.3 repeating for those that like the decimals. Okay. So let's fire up Desmos and make sure we're all good with what's happening here. I'm going to type in the f of x. Oops. There we go. We're going to look at the point 9 comma f of 9, which is 3, but we'll do it anyway. We'll do 11 comma f of 11. We'll put in the tangent line. And then we'll put in 11 comma L of 11. Okay. And now we have to readjust our window here. We want to be around, we got to go from like 9 to 11. So I don't know, this is 5 to 15 maybe. Get a nice view. And we know we're around 3, so I don't know, maybe 2 to 4. Okay. So now you see the local linearity at 9. Let's zoom in here. Okay. So just to make sure we're all dialed in on this. So from here to here, this is from 9 to 11. This is our delta x, which is our dx, which is a positive 2. We're 2 units to the right. We all good with that? Going from here to here. This is this is in green. So from here to here, this is our delta y. This is the actual change of root 11 minus root 9, which according to the decimal here seems to be like 0.317-ish. You follow? and we don't have purple for the tangent line. Now we're going to do, here's the blue. This is our dy, which we can see the dy there. We computed that to be 0.3 repeating. You follow? That was our dy was a third. And so the root 11 is roughly the 3 plus 0.3 repeating, which is 3.3 repeating, which is a reasonable approximation of that. You see how it's all tying together, folks? And then once again, here's a video. It takes you through the same process with the cube root. All right. So make sure you watch a video and give that one a shot on your own. Okay. This is something that's not in the book. I talk about it. Once again, if you go on to take multivariable calculus, you'll see this kind of stuff again. But at the end of the day, you can think of, basically to find a differential. Excuse me. If y equals f of x, the differential of y you can think of as just taking the f of x and slapping on a dx. All right. Now that's a definition. Is it multiplication? Well, in some sense it is. Is it okay to think of it as multiplication? That's what all your science and engineering people are going to tell you, right? Because in science class there is a smallest dx to worry about. That's like the Planck whatever, right? You can ask Dr. Thomas about Planck time and Planck length, right? There is a smallest meaningful length to the universe. That's the Planck length. But in mathematics, there is no smallest positive number. But essentially, if you take all the rules we had governing derivatives and you just sort of tack on the dx, they're going to work for differentials. Like constant multiple rule will work. Sum and difference works. The product rule, the quotient rule, they all work. Because all you're doing is just slapping on the dx everywhere, which you can multiply through and factor out. There's air quotes here for those who are watching the video. But they all work the way you would. And what's funny about it is, like, your book goes to great lengths in Calc 2 when we do the integration by parts to avoid this. I don't know why. So back in the day when I was taking lab courses, we used differentials to approximate error. This is no longer how it's done. Apparently, you talked, like Dr. Thomas gave me a book from his quantitative analysis courses, talked to Professor Ciferno about this. This is not how they do error analysis, but this is how I was taught to do error analysis. And it's a good application of differentials. So we're just going to walk through it because you may see this. The density of a substance rho, so this looks like P, but it's actually the Greek letter rho, is calculated by dividing its mass by its volume. All right? Have we all seen this equation before? That's density, mass divided by volume. So a scientist collects 5 plus or minus 0.5 mils of a substance and determines its mass to be 68.2 plus or minus 0.1 grams. All right, so once again, in a science setting, anytime you measure anything, there is an uncertainty. Okay? There's always an uncertainty. So she computes the density this way. She's going to use this for the mass, 68.2 grams, and this reading, and that's going to be 13.64 grams per mil. Right? However, since there was error involved in measuring both things, you have a phenomenon called propagated error. Propagated error is I've measured this thing, there's an error associated with it, but I've used that number to calculate something else. And what you want to do in science is try to get a handle on how that error propagates through your calculations. You follow? And we can use differentials to approximate that. Because when you see this, your volume was 5 plus or minus 0.5 milliliters, you can think of this part as your differential dV. You follow? That's like your error in the volume. And you think of this as your error in the mass. So what we do is we say, okay, since you've got error in mass and error in volume, what's the propagated error in density? Well, you'd find the d rho. So we're looking at rho here as a function of actually two variables, the mass and the volume. And I want to know how can I approximate the d rho? How can I approximate the error in the density? So quotient rule. Same quotient rule you had before. Low d high minus high d low. You square the bottom and off you go. Notice the d's are literally differentials. You with me or not? So then we just plug in. Volume was 5. The mass was plus or minus 0.1 grams. The mass 68.2. Volume plus or minus 0.5 mils. Volume 5 mils. So that's what's happening here. We're just plugging everything in. And since we want a conservative error, we'll assume the worst case scenario. So we're going to assume that the errors are going to combine and add. So we'll assume that we'll be on the high side, or when we measured the mass, the 0.5 we'll assume that's positive, and the 34.1 we'll assume that's negative to get the biggest difference we can up top. And so this would be a very conservative estimate of the error. You follow? It's kind of the biggest we can get. Now, it's plus or minus 1.384 grams per mil. The question is that a big deal? Is that a lot or not? So what we do is we calculate d rho over rho. So d rho is our approximate error divided by our measured density. You follow? That's going to give us what they call a relative error. We do that, we get 0.1 something, which is roughly 10.15%, which is probably in no way acceptable. Right? That's pretty huge. So you got to get better equipment or something or whatever. Now if you show this, I showed this to Dr. Thomas, and he nearly exploded because there's no significant figures on here. Right? There's no whatever. Interestingly enough, if you look at the rules of significant figures, they're very interesting because for addition and subtraction, they kind of make sense. Multiplication, they kind of make sense. Have you seen the rules for like logs and exponents? Where do those come from? That's a Dr. Henderson question, but he's retired. So, yeah, anyway, there's your homework. So what's the big takeaway today? Linearization itself is a rebranding of tangent line. If you rethink the tangent line in terms of approximation, think of this as what you know about, and this as the correction factor. This is what the differential is. That's all it is.